Okay, so like I said, we're going to address question number 16. It says compare the annual range of solar radiation at the three locations. Remember, hopefully you remember, from math that range simply means it's a calculation of how much things vary. So you're going to take your biggest value and subtract the smallest value. So it's just biggest minus smallest is what gives you range. Okay, and so that's what we're actually going to calculate down here before we answer the question. Okay. All right, so the first one we'll do is green. And if we look carefully, the biggest green value, I'm going to call it 440 or so. And the smallest green value is about 330. So the range is going to be 440 minus 330, which is about 110. That little squiggly line means approximately. Okay. Then we're going to do the red. And the largest red value looks to be, I don't know, about 500. And the smallest red value, 90, 95, something like that. We'll just go with 95. 500 minus 95 is going to give us 405. So that's the range for the red. That little squiggly line's a little hard to read. Okay, so approximately 405. And then finally we're going to do the blue. And the highest blue value looks to be, I don't know, 560, 570. I'll go with 565. And our lowest value, we have blue values that are all the way down to 0. So 565 minus 0 gives us a range of about 565. Okay. Now, we're going to go down here and do a few other things. At the equatorial location, our latitude at Singapore was just 1.5 degrees. And our variation that we just calculated, the range up here, was 110. Okay. At our middle latitude location, that was 43.5 degrees. And our range that we calculated was 405. At our high latitude location, the latitude was 80.5 degrees, and our range, sorry about that, our range was 565. So if you look, before we even really look and see what the question says, close to the equator, I have my smallest range. My sunlight, the amount of sunlight I'm getting, varies the least at the equator and varies the most towards the poles, which I think is actually what the question says. It says, yes, as latitude increases, so as latitude increases, the annual range of daily solar radiation, meaning the amount of sunlight, the range of sunlight gets bigger. So small range when you're at the equator, big range when you're away from the equator. So you're going to need to go with the annual range increases with increasing latitude. This implies corresponding seasonal variations in the amount of solar radiation available for photosynthesis in the sunlit portion of the ocean. Okay, so you're going to need to keep this little graph in mind, and we're going to go ahead and go to the next page. All right. So, on this basis, we would expect the phytoplankton population to exhibit its greatest variation through the course of the year at what location? Well, remember, phytoplankton population, assuming that, they've got the nutrients that they need. Phytoplankton population, they make their own food by sunlight. So when the sunlight isn't there, then you basically don't have a phytoplankton population. When you have lots of sunlight, then you're going to have plenty of phytoplankton. So here's the thing. If I look at my equatorial location, my sunlight varies a little bit, but it doesn't ever vary a whole lot. So I'm going to have plenty of phytoplankton probably throughout the year near the equator. But near the poles, like here in the summers, late spring, early summer, I'm going to have a whole lot of sunlight, and so I'm probably going to have a whole lot of phytoplankton. But in these other months where I basically have no sunlight, I'm going to have basically no phytoplankton. So let's answer the question. On this basis, we would expect the phytoplankton population to exhibit its greatest variation through the course of the year at polar latitudes. Because sometimes we have lots of sunshine and other times of the year we have none at the poles. Number 18, each year at higher latitudes, in response to increasing sunlight in the spring and early summer, phytoplankton populations soar. Okay? This so-called spring bloom triggers what? Okay, well, if you have increasing sunlight, then you're going to have a lot of phytoplankton. And remember, once you have lots and lots of phytoplankton, which are your producers, then you can support lots and lots of consumers, lots of heterotrophs. Okay? So, when you get this spring bloom and you get lots of phytoplankton, it's going to trigger an increase in the populations of organisms at higher trophic levels. Okay? So, basically, here's the thing. Increase in sunlight is going to give you an increase in phytoplankton. Increase in phytoplankton is going to give you an increase in everything else that is part of that food web. Okay? When sunlight decreases, phytoplankton population is going to decrease, and so are all of the other things that are tied in to that food web. Okay. Spring blooms typically last until late spring or early summer, at which time the bloom collapses. Why? Because it's used up all the nutrients that it had available. All right, so what's going to crash first? Well, no more nutrients, no more phytoplankton. So the phytoplankton population goes down first, and then when the phytoplankton population goes down, the heterotrophs are all going to follow that. Okay, so this initially causes a dramatic decline in autotrophs, okay, because there's no more nutrients to support their growth. And when autotrophs decline, that's going to be followed by a precipitous drop, meaning a really sharp drop in all of your heterotroph populations. Okay, remember that heterotrophs are your consumers, your carnivores, your omnivores, and your herbivores. Okay, and we'll pick up in the next screencast with coral reefs and coral bleaching.